Hello my dear children of class 11 science. Today again we do continue with the chapter that we were doing the last class, wave. One of the chapter under unit number 10. Okay. Now in today's class we do basically with one of the type of wave, as you have learned, is called plane progressive wave. Okay, plane progressive wave, and even we write the displacement equation, okay, in plane progressive wave. Okay, now progressive means to go in one direction, to progress in one direction. Okay, now this plane means basically two dimension. So when a wave originates from a source, this wave which originates from a source and the particle which vibrates always in what dimension? Two dimension. And two dimension is always a what? Plane. That's why plane progressive wave is simply a wave, a disturbance. Wave is simply a disturbance which propagates. Propagate means which pass through in a medium continuously, which pass through a medium continuously in the same direction. Continuously in the which direction? Same direction, without change in its amplitude. Without change in what? Amplitude. And such type of wave is called progressive wave, or we simply call as plane progressive wave. Okay. Now this progressive wave, when it start propagating in any of the direction, as I said, the amplitude of the wave remain constant. Okay, and once it start propagating from a given source, it propagates in a particular direction, in the same direction only, and without any breakage. That means it will propagate continuously. Okay, such type of wave, as I said, is called plane progressive wave. Now on the propagation of the wave, okay, on the propagation of what? Wave in any of the direction, okay, if the particle of the medium if the particle of the medium performs simple harmonic motion, okay, if a particle of the medium perform what? Simple harmonic motion means the particle oscillate with the same frequency. Particle oscillate with the constant frequency, and of course particle has to propagate with the constant amplitude. Which means the particle can perform simple harmonic motion. And in such type of motion, if the wave propagate in a particular direction with the same amplitude, and as I said, it occurs simple harmonic motion means it oscillate, the particle oscillate with the constant frequency, then the wave, that means same plane progressive wave, is also called as plane progressive simple harmonic wave. Plane progressive what? Simple harmonic what? Wave. Okay, so this is how we can understand and define what? Plane progressive wave. Now we will write the displacement equation. Okay, we write the displacement equation of this plane progressive simple harmonic wave. Okay, now for that let me just consider a plane progressive simple harmonic wave is propagating in a particular direction, say along a positive direction x-axis. What direction? Positive direction what? X-axis. So for that let me just draw the diagram. So this is a y-axis and this is what? X-axis. So this horizontal line I have drawn is called x-axis. Okay, this is your x-axis, and this vertical line which I have drawn is called y-axis. Now when I plot a graph out here, so I'll plot a graph between a displacement, okay, displacement graph. This is basically what graph? A displacement graph at an instant of time. Okay, now this point which I'll mark as a mean position, the origin, and this y-axis I consider as small letter y, and the small letter y is nothing but the displacement. Okay. Now when a particle acquires simple harmonic, plane progressive harmonic wave, and the nature of the wave will be like this. So this is the nature of what? Plane progressive simple harmonic wave. So okay, let me go do this much. So this is the plane progressive simple harmonic wave, because the particle is oscillating with constant amplitude in a particular direction and with the same frequency after every interval of time, and that is called plane progressive wave, okay, of plane progressive simple harmonic wave. Now this direction I consider, this is the direction of what? Wave motion. This is the direction of what motion? Wave motion. Means wave is propagating along with positive direction of what axis? X-axis. That's why children, the diagram which I have drawn out here is the plane progressive simple harmonic wave which is propagating, say, along which axis? Positive direction x-axis. Okay. so that we can measure the displacement of the wave at any instant of time. And this particular figure 1 shows the displacement of the wave at any instant of time. We can measure the displacement at any instant of time. So this y-axis is taken as displacement, and this y is, small letter y is the symbol of displacement. And the direction of wave is propagating along which axis? X-axis. The positive direction, what axis? X-axis. And I said already, this point O is basically marked as the origin, which means the wave start from this point. The wave is starting from this point, that is called origin. Now, in order to write the displacement equation of the particle under this plane progressive simple harmonic wave, okay, let me just consider and let me just count that the time from the instant when the particle is at the origin O. That means we start counting the wave which is propagating when starting from the origin what? O, when the time is say t. Any instant of time say t. Okay. Then the displacement equation. The displacement means y of the particle at O. Okay. At that instant of time, that t is given by y equals to a sine omega t. So this is the displacement of the particle when the time is say t. But this displacement, children, we have written in terms of what? The amplitude. The amplitude is a, and omega means what? Angular frequency. And yes, children, you have learned this relation as the displacement equation in simple harmonic motion. Yes, this is the displacement equation in simple harmonic motion. But the motion of the wave which is propagating in a particular direction, okay, particular direction, that's why with a constant amplitude, that's why this type of wave, as we call plane progressive simple harmonic wave. That's why this is also the displacement equation of plane progressive simple harmonic wave. So what is the displacement equation of plane progressive simple harmonic wave at any instant of time? Y equals to a sine omega t. And this displacement equation is true when we count the time from the instant when the particle is at the origin. Okay, particle is at the what? Origin. So that's why in this particular equation, if you see, as I said, a is what? Outer. A and, okay, let me write omega are the what? These are the amplitude. These are the amplitude and angular frequency. Angular frequency, okay, of the what? Simple harmonic motion. So I let me write it as SHM, executed by the particle. Executed by the particle. So one of the first equation, the displacement equation, directly in terms of time and the angular frequency, is written by the relation y equals a sine omega t. Now children, we will write the same displacement equation even in terms of the phase. They also called the phase angle. Okay. Now, in order to write the displacement equation in phase angle, okay, as we know that in wave motion, when wave propagates, okay, successive particles start oscillating. The successive particle means if this is one of the particle from where the wave start, then they are the other particles which are the successive particle. That particle also start oscillating. Okay, it's not that only one particle oscillates. So at any instant of time, the successive particle also start oscillating, and they also oscillate about the what position? Wave about the what position? Mean position. Okay. Now these particles, the successive particles, start oscillating about the mean position at a different time later than the preceding particle. So if one particle, first particle, start oscillating in 1 second, then in another, say 1 second, there is another particle, successive particle. The particle next to that first particle also start oscillating about the mean position. So what happens once the time start passing out, the successive particle keep on oscillating about the what position? Mean position as the what particle? Preceding particle. So under this condition, what happens, children, that as we go or as we move away from O, from the point where the particle have start oscillating, okay, then the phase lag, phase means the angle, okay, the position of the particle which are vibrating, okay, the phase lag of the oscillation of the particles with respect to the particle at O, and this phase lag of the oscillation particle goes on increasing. That means the particle which are far from this particle at O vibrate after later time, okay, when the particle already start vibrating at O. That means there is a lag in the phase. There is a lag in the phase of the particle, succeeding particle, which start vibrating from with respect to the particle at O, and when we go away from the particle at O. So when we go away from the particle at O, okay, then whatever particle vibrate when we go away from the particle O, they always have a phase lag of the vibration or oscillation of the particles. Okay, so in this case, what happened? When we measure the displacement of the particle, say at certain distance from O, then that particle will have a displacement, but with a certain later time, at certain angle later, or with a phase lag, let me use the word, a phase lag with respect to the particle which was displacing at O. Displacing at O means the displacement at the origin. Now, in order to measure the displacement of the particle other than at O, okay, in terms of this phase difference, or also called phase lag, okay, let me take the particle which is displacing along positive x-axis, okay, other than what? O. And for that, let me just consider there is a phase lag of the particle, and that particle is somewhere out there. So let me just consider somewhere at this point. So let me consider there is a particle at P, okay, particle at P, and which is already have a displacement, okay, which already have a displacement with respect to O, and that displacement I consider as, say, x. I mean, this is the position or the distance of the particle which is displacing, okay, along the axis, okay. But the particle which is according to displacement, okay, at a later time with respect to particle at what? O, acquire a certain phase lag from this particle at O. The particle at O means the particle from the what? Origin. So under this case, the displacement of the particle P, okay, at any instant of time, okay, is also written in a similar manner. So children, I have considered already in the diagram that there is a particle, say P, from the origin, say at a distance x, that is along positive x-axis. That particle, say, start oscillating at any instant of time, say t. Then definitely that particle, there is a phase lag of the particle P from the origin, and that phase lag I consider, say, phi. So this phi is the phase lag of the particle, which particle P, which is displacing, okay, producing a displacement with respect to the origin, okay. So under this case also we can write the displacement of the particle. We write the displacement particles. I write down therefore the displacement of the what? Particle. And which particle? P, a particular particle, say P, okay, at any instant of time. At what? Any instant of time, say t is given by y, right, in the similar manner, y equals to a sine but omega t minus phi. See, this minus sign means that particle is lag by a phase angle phi with respect to the particle which was displacing at the origin. That's why this is the displacement of the particle P, which is at a certain distance x at any instant time t. Okay, so y equals to a sine omega t minus phi. Okay, y equals to a sine omega t minus what? Phi. Now children, we can write this phase angle in terms of that distance of the particle from the origin. Okay, so in order to write that, let me just go back to the diagram. Now if you look at this diagram, children, the particle have oscillating from this point. So when particle is at this point, when the particle at this point reaches, okay, then when the particle from this origin, okay, start vibrating, and when the particle vibrate at this point, then this makes one complete oscillation. Now for one complete oscillation, the angle, the phase angle or the position of the vibrating particle with respect to origin is basically marked by 2 pi. How much? 2 pi. So for one complete oscillation, the phase the position or the phase angle of the particle is with respect to the particle at the origin is how much? 2 pi. 2 pi means how much? How much degree? 360 degree. Okay, 2 pi equals to how much degree? 360 degree. And at that time, whatever distance covered by the particle, okay, to have one complete oscillation, as you have learned, is also called wavelength. Also called what? Wavelength. But out here we are calculating the displacement of particle p other than this point, and that particle is at a distance x from the origin. Okay, so we can write now the same displacement equation in terms of this distance where the particle is displacing from the origin, okay, at a distance x. Now children, for one complete oscillation, if you remember this, the phase change from the particle at O to that one complete oscillation is how much? 2 pi. So what is the phase change or phase difference between the particle for one complete oscillation particle? 2 pi. 2 pi means how much? 360 degree. Okay, so under this phase change of 2 pi, so what is the displacement? The distance of the particle from the origin, and I don't, not displacement, sorry, the distance of the particle from the origin, and that distance is equals to what? Lambda. That distance equals to what? Lambda. Which means, I don't know now, since for distance, and this distance is also called wavelength or distance for how much? One oscillation, for one complete oscillation. One complete oscillation. And that wavelength distance, or that distance is lambda for one complete oscillation. What is the phase angle? 2 pi. So if the phase difference or phase angle is 2 pi for one wavelength or one distance complete oscillation, then I write down the phase angle. The phase, okay, we can use the word phase change. The phase change for one distance. Okay, let me use the word one distance. Okay, unit distance. Let me use the word unit distance is equals to 2 pi by lambda. This is just like a unitary method. Okay, but what is the actual distance we are calculating the displacement particle from the origin? That is x. So I write down therefore the phase change for, okay, x distance. What distance? X distance from the origin. From the what? Origin is given by phi, and that angle phi is nothing but 2 pi by lambda into what? X. So for unit distance from the origin, this is from the origin, the phase change is how much? 2 pi by lambda. So phase change for x distance of the particle from the origin will be phi equals to 2 pi by lambda into x, which means we are calculating the phase change from origin to the particle at p at a distance x. Okay, so we are calculating the phase change between the particle at p and with respect to the origin, and that is at a distance what? X. And that phase change I have already marked by letter phi, and that phi only we measure as 2 pi by lambda into what? X. So under this relation, if you see, this phase change can be measured by 2 pi by lambda into x. So in this relation, this 2 pi by lambda is basically a constant. This is basically what? Constant. And we call this constant as propagation constant, and we mark by letter k. So we can replace by k, called what? Propagation constant. This is basically called as propagation constant. So I can write the same phase as kx. So k, this 2 pi by lambda I replace by k, so it will be phi equals to kx. That means the phase change can be expressed in terms of propagation constant into the distance of the particle which producing a displacement. Okay, so I can write now the relation as, therefore, y, displacement y equals to what? A sine omega t minus, now this phi I replace by what? Kx. So children, look at it. The displacement of the particle at a distance x on the positive x-axis, okay, from the origin can also be written as y equals to a sine bracket omega t minus kx. So this displacement equation which I have written in terms of a constant called propagation constant. So this is also one of the equation that measures the displacement equation in terms of what? Propagation constant. But this relation is true when the wave propagate in the which axis? Positive x-axis. That means the wave is traveling along the positive direction what? X-axis. But it doesn't mean that the wave propagate only in positive direction x-axis. The wave can even propagate in negative direction x-axis. Under this condition, when the wave travels along a negative direction x-axis, okay, so the relation can be written in a similar manner. So y equals to a sine omega t plus kx. So I just put what sign? Plus sign. So this is for the wave which is propagating along negative direction x-axis, and this is the wave which is propagating for positive direction what axis? X-axis. This is for positive direction x-axis. This is for positive direction of x-axis. Okay, so these are the two equations even we have derived when two equation for displacement equation, okay, of the plane progressive simple harmonic wave which can propagate in any of the direction of x-axis. It can be along positive x-axis or negative x-axis. Now children, we write the similar equation, okay, in terms of other quantity also, and that we do continue in the next YouTube video.